In this video, we're going to discuss binary integer linear programming using a road trip planning example. And we're going to get familiar with the modeling flexibility that is provided to us by the binary variables in linear programming formulation. So we're going to be talking about multiple choice constraints, mutually exclusive constraints, K out of N constraints, conditional constraints, and co-requisite constraints. So here I have the example, the road planning example. And in this example, we're assuming that we want to plan a road trip. Each one of you imagine that you guys are gonna plan a road trip. You want to rent a car with 5 seats. So you're gonna be there, and you have 4 more seats. So 4 more possibility. And then you want to pick among a list of 7 close friends that you have. So you want to make sure to invite those 4 people that give you the maximum fun during your road trips, right? So for each person, so I just named them A to G. So each one of these letter stands for, let's say, the name of your friend. A, the first friend; B, the second friend; C, the third friend; and G, the last friend, the 7th friend. For each one of them, we know the gender, we know whether they can drive or not, and we also know how much fun we can get if they're present. For the fun, it's actually a very tricky function. We're assuming that it's first of all, it's a linear function. Second of all, the fun that we get from each person is independent of the actually other people's presence. So let's say if we get 3 units of fun from the presence of B, friend B, that 3 units is not going to be affected if, for example, D is present or not. So everybody's the fun that we get from each person is independent. It's only dependent to their own presence. All right. So we want to maximize the fun that we get out of the road trip. And then we have a list of constraints. And in those constraints, hopefully, we want to cover all those examples that we just mentioned. All right. The co-requisite, the conditional, K out of N, and so on and so forth. But let's just go ahead and define the decision variables. So decision variables is going to be, I'm gonna insert one row here. The decision variable, or you know what, let me just put it right here. I just define it here. We're not gonna solve this. I just wanna show you how to formulate this problem. Variable. So there are 7 people. And the way we formulate this problem is, so the question that we want to answer here is that which person is going to be invited at the end of the day. We want the list of people who are going to be invited. Out of these 7 people, we're going to pick 4. Who are those 4 people? That's our question that we want to answer. But then the way we model this, if we want to solve it using integer linear programming, in those cases, in cases like this, we model this as a binary decision variable. So for each person, we need to make the decision whether I'm going to invite the first person or not. So 0 or 1, 1 being invited, 0 not being invited. And then same thing for the second person, same thing for the third person, and all the way to the end. So I would have to make this decision for every single one of them, whether or not the person, whether or not person I or friend I, if we call them, if we count them like I being the, like 1 being the first person and 7 being the last person, whether or not friend I to be invited. All right, so that's the decision variables. That this is the list of decision variable, and it's going to be, let me just add it right here. It's going to be 1 if invited, 0 otherwise, 0 if not invited, right? All right. Yes. So whether or not each person, each friend is invited. And we have to define a separate decision variable for each one of them. If we want to use binary meaning that they can take either 0 or 1. All right. So that's the decision variable. Now the objective that we want to maximize would be fun, right? So we want to maximize the fun. And how do I write the objective function for the fun? So if person A comes, and I'm going to use actually, so I didn't denote, let me just get out of here. So I'm going to call them A, B, all the way to G. So each letter, so I'm going to use corresponding letter to same letter actually for calling the decision variable corresponding to each person. So objective function is going to be the maximum of fun. So I'm going to get 2 units of fun if A comes. So if I take 2 times A, now A can be 0 or 1. If A is 0, it means that person A, friend A, is not going to be there. So 2 times 0 is going to be 0. So I won't get any fun from person A if he or if he is not there, right? But if A is 1, meaning that A is present, 2 times 1, it's going to be 2. I would get that fun, 2 units of fun if A is present, plus 3 times B plus 3 times C plus 4 times D plus 5 units of fun if E comes, 5 times E plus 2 times F plus 4 times G. So that is the objective function that I want to maximize, the fun that I want to get. If none of them come, if I don't invite anyone, my fun is going to be A is going to be 0, B is going to be 0. All of them are going to be 0. So 0 times any value is going to be 0, and sum of zeros is going to be 0. So no fun if nobody is invited, right? If I invite all of them, if I mean, I didn't have the constraints of inviting 4 people, the fun that I could get was 2 plus 3 plus 3 plus 4 plus 5 plus 2 plus 4. All right, but of course I have some constraints that I have to respect. So now let's go ahead and look at these constraints. So for the first one, maximum number of people to be invited should be less than 4. I can't invite more than 4 people. I can invite less than 4 people, but I can't invite 5 or 6 or 7 people, right? So the total number here, if I want to make it equal to 4, I can do it. If I want to make it less than or equal to 4, that's also okay, since my objective function is maximization. So the total number of people that are invited, I'm going to write it down, but think about it. A plus B plus C plus D plus E plus F plus G. So I would say this is the sum of my decision variable. It's going to give me the number of people who are going to be invited. If all of them are invited, it means that all the decision variables are going to take 1. So 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1 is going to be equal to 7. If only A is invited and none of them are invited, 0, 0, 0, 0, 0 plus 1, it's going to be 1. So taking this sum will always give you the number of people who are invited to the party or to the road trip, right? So that is going to be the number of people that are going to be invited. And I want this to be less than or equal to 4, right? 4 is the maximum number of people that are going to be able to fit in the car. I can't go more than 4. I can't go with more than 4. So this is actually, if it was equal to 4, it was called K out of N. All right, K out of N, or in this case, 4 out of 7. It's actually 4 out of 7 in this case. If I said if this was equal, I wanted to pick exactly 4 people out of 7 people. This is how you write it. Sum of all of them equal 4, or sum of all the n, capital N, equals to K. If you want to pick K out of N, sum of N objects equal to sum of N decision variables equals K. That's how you pick exactly K out of N. But if you want to take at most K people out of N, so this is at most K out of N, then that would be less than or equal to 4. This would, let me just call it at most K out of N. Exactly K out of N is equal. At least K out of N is greater than or equal to. All right, so let's just move on. Next one, A and B are couple, either both or none of them. I want you to pause the video and think about it. How do I write a constraint like this? A and B are couple. So if I want to consider all cases of A and B, so A can be 0. No, don't invite A, don't invite B. Invite A, invite B. Don't invite A, invite B. Invite A, don't invite B. So this is the list of all the possible scenarios, right? So let me just, I'm going to use this space for, or maybe put it here, here maybe. And all right. A and B, and this is the list of all the possible cases. You can invite both of them. You can not invite, you can invite none of them. You can invite only B or only A. So 4 cases are possible. Now, we're saying A and B are couple, meaning that I don't want these 2 cases. I want to rule out these 2. Let me just use if I say A and B are couple, I want to, so these ones are okay, but these 2 are not acceptable. So I need to write down a constraint that'll make sure that I only get these 2 and rule out these 2, right? Think about it. This is actually called a co-requisite. Co-requisite type of constraint. And the easiest way you can model this is by saying A equals B. So that's how you, for binary variables, how you model a co-requisite constraints. A equals B. So this will pass if you have a constraint like that. It allows this one. It allows the second one. It doesn't allow the third one. It doesn't allow the fourth one. So it's going to rule out having this constraint in your model. It's not going to allow these two last cases to happen, right? And again, it's going to be called co-requisite because you want them to take the same values. You don't want them to be different, right? The next one, at least one extra driver needed. So the next three are this more or less the same, except that here we had at most k out of n. Here in the next cases, we have at least 1 out of 7, right? So at least one extra driver. Of all those people who can drive, we want to have at least one of them. Who are those people who can drive? B, E, and F. So B plus E plus F, I want at least one of them to be present, to be invited. So at least 1 out of 3. All right. At least one female to be invited. At least one female should be invited. So who are my female friends? B, C, D, and F. So B plus C plus D plus F, they should be, at least one of them should be invited. Again, at least one out of, this time 4, right? I need 1 out of 4, B, C, D, and F, at least one of them to be invited. At least one male should be invited. So I want to have a blend of genders, right? So I want to have both females and males in my road trip. So here, males, A plus E plus G greater than or equal to 1. So that is, again, at least 1 out of 3 type of constraint. All right. Next one, C and D cannot be invited together. So this is actually called a mutually exclusive type of constraint, mutually exclusive. You can't invite, in this case, we have 2 people. You can't invite more than 1 person out of 2 people, but it can be true for multiple. I mean more than 2 people. Let's say if you had 5 people and you said, I can't invite more than 1 person. So that is called a mutually exclusive, right? And in those cases, so mutually exclusive, let's say I'm going to change this to C and D, and I'm going to get rid of this. So mutually exclusive does not allow this one. You can't have both of them together. It's okay if you don't invite any of them. It's okay if you invite only C. If it's absolutely okay if you only invite C, but you can't have both of them. So the way it works, the way you just make sure that this does not happen is by doing this C plus D less than or equal to 1, right? So this, the first case can pass if you have this constraint. So this constraint allows the first case to happen, allows the third case to happen, allows the last case to happen, but it'll just doesn't allow this one to happen, which is exactly what we want. So mutually exclusive, it's basically when you have, let's say, x1 plus x2 plus xn less than or equal to 1. So at most, one of these people can be selected, or at least one of these projects, depending on the case, depending on the type of your decision variables. At most, one of them can be present. At most, one of them can be selected. So this is how you write a mutually exclusive type of constraint. All right. But in this case, we wanted to pick out of 2. Okay. And all right. So this is mutually exclusive. If we have, I'll get to that. We have another term to define. It's multiple choice. And I'll get to that. If we had exactly 1 out of n, it's also called a multiple choice, where you need to pick 1. So let me just 1 out of n. It's also called multiple choice constraint. Multiple choice, exactly 1. If I say out of the people that are driving, pick just one of them, right? That would be B plus E plus F equals 1. So that is a multiple choice. So you have among 3 drivers, you want to pick 1. So it's multiple choice. It's called multiple choice. And mutually exclusive, only 1, at most 1 out of a couple of people or more than 2 people. At most 1. They can't be together. D comes, the next one, the next constraint, D comes only if E comes. So this is actually a special case here. This is called conditional. One of them has a condition. So it's a conditional type of constraint. Let me just update this, D and E. It says, let me get rid of the shade here. So it says D comes only if E comes. So D comes only if E comes. So this is fine, but this does not pass. So this constraint that we're doing right now, D comes only if E comes. You can't have E invited and you can't have D invited and not E invited, right? So D doesn't come without E. So there is a condition here. D comes only if E comes. So if D wants to be 1, then E has to be 1. So it's a conditional type of constraint. Example of conditional in business would be if you have multiple phases of a project. Let's say if a project has 2 phases, you can't invest in the second phase of a project unless you have made investment in the first phase. So the second phase of a project usually, by definition, is conditional on undertaking the first phase of the project. So that is a case of conditional. So, and the way it works is D, which is the second phase, is the follower, should be less than or equal to E, less than or equal to the leader, less than or equal to the first phase. All right. And again, just check here. The first case, none of them invited, can pass. So that's fine. The second case can pass 2, 1 and 1. That's absolutely fine. 0 and 1, 0 and 1. Again, that passes. This one passes. This one doesn't pass. D cannot be greater than E, cannot be strictly greater than E. D is follower. It has to go after E. E has to be there, right? So that is how you write down a conditional type of constraints in binary integer linear programming formulation. Next one, E comes only if both A and B are invited. So we're on this one. E comes only if both A and B are invited. So let me just add another player, A, B, and E. So no fill, and then 0, 0, 0, 0. So if we have 3 players, there will be 8 cases, 8 possible cases that can happen. And here I have all the cases. None of them invited. Only A and B invited, and E not invited. Only B invited. Only A invited. Only E invited. All of them invited. Only B and E invited. Only A and E invited. So 2 times 2 times 2, 8 cases in total, right? So now the last one, E comes only if both E and A are invited. It's again a special case of conditional, right? It's conditional, but it's different from the previous one. It's here, what I want to show you here is that it doesn't have to be this. It doesn't have to be as simple as this one. Uh, I'm talking about the modeling flexibility that binary programming gives us. You can have lots of different possibilities. You can have lots of different conditions, and you should be always able to find an innovative way to model it using the binary variable. So here we want to do this. It's a little more complicated than this, but if you have this, and if you just try to rule out the bad examples and come up with a linear, it's very important to come up with a linear constraint that rule out the unwanted cases, then you're good to go. You can actually formulate any condition, any real case. E comes only if both A and B are invited. E comes only if, so this is not good. We don't want E comes without A and B coming. This is perfect. E comes, both A and B are invited. You can invite E and only invite A or only invite B. So none of these two cases are acceptable, right? 1 means being invited, 0 means not being invited. So these cases are all fine. I mean, if you don't invite E, doesn't matter what you're doing with A and B. But if you want to invite E, that can only happen if both A and B are invited. Other than that, they're not possible. So you now get to write a constraint that rules out the 3 cases. So now I want you again to pause the video, think about that example. How do you write a constraint that makes sure that none of these cases is going to happen? Think about it. I'm going to write down the answer here, but that is not the only way. I'm sure you can find other ways that that can actually come up with the same result. But again, you just need to make sure that you go with linear forms. And it's always better if you can go with the least number of constraints. You don't want to add too many constraints to your problem. So 2 plus E, 2 times E less than or equal to A plus B. By adding these constraints, this one is fine. This one will pass. This one will pass. This one will pass. 2 times 0 less than or equal to 1 plus 0 absolutely passes. This one will pass. This one does not pass. So 2 times 1, 2 cannot be less than or equal to 0. For this one, 2 cannot be less than or equal to 1. 2 cannot be less than or equal to 1. But this one again passes because 2 times 1 is indeed less than or equal to 1 plus 1. All right, so that's the innovative way that you can write. You can get what you want with only one linear constraint. All right, and you always need to make sure to have equality in your constraints. All right, I mean less than or equal. You don't want to go with strictly equal or strictly greater than, um, for the sake of your solver, for the sake of your formulation to be able to be solved. You want to have a convex feasible region, right? So that having the equality always in your sign will make sure to get that. And actually in the solver, you only have the equality sign. All right, so that is how you write it down. Let me just go back to my, let's just show you how the solver works. So I think we covered everything. We covered co-requisite, conditional, K out of N, multiple choice, and mutually exclusive. Now, let me quickly show you. I'm not going to solve this. It's not guaranteed that this one has a feasible answer. But let's say if this is the decision variable, I just want to show you how this works. So if these are the decision variables, when you're on solver, you can have your define your the objective function based on the decision variables. You can have you can define all the constraints, left hand side, right hand side, and the signs. But then there's only one thing, and in our formulation, the last piece that I actually already mentioned, if I go back to my list of decision variables, or I already indicated that they are binary. They're all binary decision variables. When you're on the solver, again, I'm not going to set it up, but this one, you have to make sure to define these decision variables as binary, right? Just pick bin and it'll make sure to define them as binary. Okay, so I did not. Okay, so here I have to first define the decision variables and then have them be defined as the binary. Again, I'm not going to solve it, but this is what the only additional type of constraints that you have to add on top of the normal constraints that we knew from the linear programming modeling and formulation.